Okay, so this problem says the following. Let M be a left R module. Suppose that phi from M to M is an R module homomorphism that satisfies phi squared is equal to phi. Then there are two parts. Part A says prove that M and the direct sum of the kernel of phi and the image of phi are isomorphic as left R modules. And part B says to produce an explicit example of a ring R, a left R module M, and a non-zero R module homomorphism phi that's not the identity map on M that satisfies the condition from part A that phi squared is equal to phi. Okay, so let's start with part A. So part A. So we need to show that M and kernel of phi, direct sum, image of phi are isomorphic left R modules. So let's define the R module isomorphism. So let's define psi from M to the direct sum of the kernel and the image by, well, let's send M to the ordered pair M minus phi of M, comma phi of M. Okay, so the first thing we need to make sure is that this is well defined, but it is. So well defined. So clearly phi of M is in the image of phi. Uh, what about M minus phi of M? Is that in the kernel of phi? Well, phi of M minus phi of M. So M minus phi of M is just some element of M, so we can apply phi to it, and we get, because phi is a R module homomorphism, in particular, it's a additive homomorphism. So phi of M minus, this is equal to phi of M minus phi of M, right? A R module is an abelian group, and phi being an R module homomorphism means that it's a um, under addition, and that means that it's an additive group homomorphism. So we have this. And now the assumption of the problem is that phi squared is equal to phi. So that is equal to phi of M minus phi of M is the same as phi of M. And so that now is 0. So M minus phi of M is indeed in the kernel of phi, and clearly phi of M is an element of the image of phi. Okay, so we've defined our map in a legitimate way. Now we need to show two things, that it is an R module homomorphism and that it is a bijection, and that will show that it's an R module isomorphism. Okay, so let's do that it's an R module homomorphism first. So uh, we must show we have to check that psi is an R module homomorphism and that it is a bijection, so injective and surjective. Okay, so let's do our module homomorphism first. So observe that if x and y are elements of M, then psi of x plus y is x plus y minus phi of x plus y, comma phi of x plus y, which is then uh we just are using the fact that phi is a R module homomorphism, so we're gonna rewrite things. This is gonna be x plus y minus phi of x minus phi of y, comma phi, break it up on the right as well, phi of x plus phi of y. Okay, and now the direct sum, uh, it's it's an R module homomorphism. I mean, sorry, it's a left R module. It's an abelian group under addition, and the addition is component wise. And so this is equal to x minus phi of x, comma, phi of x plus this addition is taking place in the direct sum, the tuple y minus phi of y, phi of y, and that is psi of x plus psi of y by the definition of psi. Okay, so we have that psi is an additive group homomorphism, but the other thing we need to check, um, and also we need to check that R, you know, so okay, this should be quantified for all x and y in M. We also need to check that for any R in R and x in M, R acting on psi of x is ought to be the same as psi of R acting on x. Well, this is so again in the um, right, so this is R acting on the tuple x minus phi of x, comma phi of x. Okay, and then the direct sum as a left R module, the action of R is again component wise. So this uh is going to be R acting on this, comma R acting on this. And because just by the module axioms, that will be Rx minus phi, sorry, minus R phi of x, comma R phi of x. And now since phi is a R module homomorphism, we get to move the R inside. So we have that Rx. This is the order pair Rx minus phi of Rx. And right, so R phi of x is we know phi of Rx. And this now, if we just look at the form it has, is psi of Rx. Okay, so this tells us um, much of what we need, namely, uh, so psi is an R module homomorphism, right? And now we need to check that it's a bijection so that we actually have an isomorphism. So let's check that it's injective and that it's surjective. We'll do injective first. So now suppose psi of M1 is equal to psi of M2. Then, well, what is psi of M1? It's M1 minus phi of M1, comma phi of M1. And that has to be equal to psi of M2, which is M2 minus phi of M2, comma phi of M2. Okay, let's refocus. All right. Well, now Kuratowski tells us that um, M1 minus phi of M1 is equal to M2 minus phi of M2, and phi of M1 is equal to phi of M2. Okay, but now we just have additive cancellation in this abelian group. So, um, adding phi of M1 to both sides of this equation, when phi of M1 is equal to phi of M2, uh, we get this by additive cancellation. M1 is equal to M2, and that tells us that psi is injective. All right, let's do surjective. Now let AB be an element of the direct sum, kernel of phi, direct sum, image of phi. Okay, well, so we need an element that maps to AB. Well, what do we know about AB? Well, uh, so then A is in the kernel of phi, and B is in the image of phi. So A being in the kernel means phi of A is equal to 0, and B being in the image means there exists an M such that phi of M is equal to B. Okay, so what's our element going to be our element of M that maps to the ordered pair AB? It's going to be uh, A plus phi of M, which I guess is A plus B. But it's going to be so phi, or sorry, psi of A plus B is equal to psi of A plus phi of M, because B is phi of M. And that's equal to A plus phi of M minus phi of A plus phi of M, comma, phi of A plus phi of M, one more parentheses. And that will be equal to, uh, well, A plus phi of M minus phi of A minus phi of M, comma, phi of A plus phi of M, close, close. one more close. Yes. Okay. And now this is, well, remember, phi of A is 0, and phi squared is phi. So phi of M is just phi of M. So what happens here? This is 0. So I'll write one more step. A plus phi of M minus 0 minus phi of M, comma, phi of A, which is just 0. Sorry, 0 plus phi of M. And that is clearly A, comma. Phi of M is B, remember? So that's just AB. All right. So psi is surjective as well, and therefore psi is an R module isomorphism between M and the image of phi, or kernel of phi direct sum image of phi. Okay, so that completes part A. Now let's move on to part B. So recall for part B, we were asked to produce an explicit example of a ring R, a left R module M, and a non-zero R module homomorphism phi that's not the identity uh, that satisfies phi squared is equal to phi. And this is not actually so bad. So let's choose this example. Let R equals Z. And let M be uh, Z mod 6Z under addition with, if M is going to be a left R module, we have to say what the action is. So with the action R cross M given by uh, N acting on M is going to be NM mod 6, N times M mod 6 for N in Z, M an element of Z mod 6Z. Okay, so you can check that this is, of course, a R module homomorphism. Or sorry, uh no, sorry. So far we've just you can check that this is that M is a left R module, right? We can check the module axioms. Um so now we want to define an R module homomorphism that's not the identity and that's not 0 from M to itself. So define phi from M to M by phi of M is going to be 3 times M mod 6, of course. Okay, so then clearly this is not the identity. Right? It'll send 1 to 3 and 2 to 0 and 3 to 3 and 4 to 0 and 5 to 3, right? 0 to 0. Um, it's not the identity. It's not the 0. Uh, R module homomorphism. Uh, let's check that that is an R module homomorphism. So R phi of M is R times 3M mod 6, which is 3RM mod 6, which is phi of Rm, and also phi of x plus y is equal to 3x plus y mod 6, which is 3x plus 3y mod 6, which is 3x mod 6 plus 3y mod 6, which is phi of x plus phi of y. So phi is an R module homomorphism. And then the last thing we need to show is that phi squared is itself. So phi of m is 3 times 3m mod 6, which is 9m 6, which is 3m mod 6, which is phi of m. And so this phi for this m and this r satisfies the criteria for part B. And that completes this problem.